Hello and welcome to this video on biasing the BJT. We start with the simple base bias and the simple circuit shown. And there's not much in there, so we want to ease you in with the maths. The first thing we do is we say that for the sake of our models, we will have the voltage between the base and the emitter at 0.7 volts. We are going to assume that that's a constant 0.7 volts between the base and the emitter junction of the transistor. And actually, that's a fairly accurate representation because it doesn't vary very much. And the little bit that it will vary based on the way the transistor is operated is not likely to cause your results to have a significant amount of error. Okay, so let's continue that. Let's just always assume that we have 0.7 between the base and emitter leads. Okay, now we write a couple of equations. Basically, we want to write equations for all of the currents in all leads of the transistor and the voltages. The 3 currents and the 3 voltages, making 6 total things we want to find in this video. So the first one is the emitter current, and the emitter current is going to be the sum of the collector current here and the base current here. As you can see, we have 2 paths that the current can flow, and then it joins together to ground. So basically we have whatever is in this leg and whatever is in this leg added together. That's all we're saying. And the second, our second statement of the collector current here relates it to the base current by the quantity beta. Beta is the current gain of the transistor. So very small current here, we have a fixed amount of gain. So we multiply that and we have that current here flowing in the collector. Now we make another statement for the emitter current in terms of the base current. It's useful to do that since we have basically beta times IB and another IB, and they're joining together here. It's obvious we are going to end up with beta plus 1 IB as the emitter current. So that's just an alternative statement for the emitter current. Now let us look at the voltages. The voltage on the emitter is going to be 0 because it's connected to ground, and we measure all voltages from ground. The voltage on the base will be our fixed voltage of 0.7 volts, and the voltage on the collector will be the V minus whatever voltage is across the resistor. The voltage across that RC will be the resistance RC times the current, which is beta IB. We subtract that from V, and that will give us our VC. Now, the voltage V is going to be the sum of 2 voltages, the sum of the voltage across here, the 0.7, plus the voltage across this resistor, which is, of course, the current flowing through it, IB, times the resistance, RB. That will give you the voltage across there, must add up with 0.7 to make the total voltage V. Now we bring the VBE over to the other side and make it negative since it's a constant. So our constant power voltage minus the VBE is going to equal the resistance times the base current. And the last thing we do is to make the base current the subject, we divide by the RB, and that gives us the formula to be able to find our base current. And once we find IB, the complete package is known. We know all the currents, we know all the voltages, and that's about as hard as it gets for the simple base bias. So let's get ahead now to the emitter stabilized bias. As you look at the emitter stabilized bias, you see we've added one resistor and the emitter is no longer connected to ground. But this is a very useful addition, because these transistors operated like this is far more reliable, and our progression of biasing the BJT is in making the system more stable and reliable, and the operation of the circuit less dependent on beta. So let's take a look. Like before, we are going with our 0.7 volts between the B and the E. And likewise, we still have the same relationship for the emitter current as well as the collector current. And the only change here begins when we look at the voltages. Okay, the voltage, the collector voltage is the same. The base voltage now we will define as the V minus whatever is dropped across the IBRB. And the emitter voltage, it will have a voltage this time, will be the emitter current, which is beta plus 1 times IB times the emitter resistance RE. If you notice, the only thing we have to find now is the base current. The base current is always the one that requires the most calculation. Now, as we can see, our system moves to 3 terms because we have to add the voltage across the emitter resistor, then we have to add the VBE, then we have to add the voltage across the base resistor. So 1, 2, 3 voltages as shown there. So we substitute beta plus 1 IB for the emitter current, because that gets all of everything into terms of IB. We bring the VBE over to the other side just as we did last time. We collect up the common IB out of the other terms. And finally, when we divide by what's in the brackets, we end up with our base current, which is based on the same approach we took in the simple circuit. It's just that we now have more terms in the denominator of the fraction. All right, so we move on now to the voltage divider bias. The voltage divider bias is a further attempt to stabilize the circuit against any changes in the transistor parameters. Because transistors cannot be manufactured to a very high degree of precision, the parameters of the transistor can vary quite widely, and we should be able to stick any small signal transistor of a similar type in there and get similar behavior. So what these external resistors are beginning to do now is to stabilize the operating voltages and currents of the transistor, which we have been calculating up to this point in time. So clearly, the more resistors we are adding, the more reliable the circuit becomes and the less dependent on beta. Okay, so this time around we are going to write down our equations. We don't need to go through them. The first 3 are exactly the same as we did before. And the only thing now that changes in this circuit will be the base voltage here. We have to use Thevenin's equivalent circuit to work it out. So we leave it open for right now, and we'll just write down our emitter voltage. Now, if we were to cut the circuit there, or break the circuit, break the wire at that base where I have the X, and replace the circuit to the left of the X with a Thevenin equivalent circuit. I hope you know about that, but if not, you have to do a little research. The Thevenin equivalent circuit produces this configuration. When we narrow down the circuit, we have a Thevenin voltage, a Thevenin resistance that feeds into that circuit to the right of the X, and then we're looking at the emitter and base circuit of the transistor, and that's the circuit on which we are going to apply Kirchhoff's voltage and current laws. All right, so as you look at that circuit, you can see that VB, which is the voltage at the base, is going to be VTH, the source voltage, minus whatever voltage is dropped across RTH, which is just RTH times IB. So that now should be self-explanatory based on that little diagram in green. So VTH now is just our V across the voltage divider of R1 and R2. So R2 over R1 plus R2 is just the voltage divider formula. That's the voltage that's at the X. And it's a fraction of the V. So the VTH is a fraction of the source voltage V. And the RTH is found by making the dead circuit. I'll explain that in a minute. But basically it is R1 and R2 in parallel. So that's the parallel formula there. R1 times R2, R1 plus R over R1 plus R2 is the simple parallel formula for two resistors. And now we're in a good position to be able to find out what IB is. So we write another circuit here in terms of IB, as you can see. And this is the entire thing from, we're going right around that little, we're going right around this little thing here. So starting over here, we have RTH times IB. Then we have VBE, add that voltage to that. Then we have beta plus 1 IB times RE. So basically all we're saying here in that equation is that the voltage across this plus the voltage across this plus the voltage across that must add up to VTH, which is just basically another way of stating Kirchhoff's voltage law. Okay, so we just have to bring around those terms. We just have to take out the IB and move the VB E across to the other side, and looks very similar to what we had before. And there we have found our IB. Now we're going to talk a little bit more about the Thevenin equivalent circuit as it relates to the voltage divider biasing. I've done it again over here so I can explain it a little better. The first diagram here shows that we're starting with this voltage and it's being divided down across here so that VTH is a fraction of V, and that is just R2 over R1 plus R2, so that explains that one. And over here now we see that when we remove the voltage source entirely, it's replaced by a piece of straight wire. This is because the internal resistance of voltage sources is extremely small. So if we kill the voltage source, we call it killing it, to zero, then there will be no voltage there, but it will behave exactly as a piece of wire. So this concept of dead resistance, or it just applies throughout electronics actually, dead resistance. The dead resistance here when we kill the voltage source is just the parallel, as you can see, parallel combination of R1 and R2, which makes our RTH. All right, so we come now to the collector feedback bias, which is the last one we have to deal with for today. And as you can see, the big difference here is that we have taken the base resistor, we've taken it from the collector instead of from V. So this would be very similar to the emitter stabilized bias, it would be identical to the emitter stabilized bias if we were to take out that wire and just move it up to V. So this is just a slight change here, and it provides some sort of feedback from the collector circuit to the base circuit, but is a further method to stabilize and make the transistor more stable. Stability revolves around thermal stability as well as basic instability that comes about as a result of gain. So by lowering the gain with negative feedback, we are actually making the circuit more stable, and this is a negative feedback mechanism, but you don't have to understand that aspect of it right now. So let us just get ahead here, and we notice that our equations are pretty much the same again up to this point. And we're just repeating equations. So this is the same as it always was in the previous one. And we now look here at the VC. That's the one that is slightly different. We take V minus beta plus 1 times IB. Remember, it was beta IB before. Well, it's now gone to beta plus 1 IB because in this particular circuit, the same current is flowing through the emitter as is flowing through the collector resistor, right? So from a voltage point of view, we have beta plus 1 IB here, and we have beta plus 1 IB here, and then it splits, and beta IB goes through the transistor, and 1 IB goes through that there. So by moving the split from up here to up here, we've slightly increased the current flowing through here, so make it identical. So basically, we have identical current now flowing through RC as through RE. So that is the change in that circuit. And what we do here now is gives us our VB. We simply subtract whatever VC worked out to be. We subtract the voltage across that resistor there, IB times RB. IB is the base current, and we multiply it by RB to find the voltage across that. We subtract it from VC, and that becomes VB. Okay? And finally, VE is the same as it was in the emitter stabilized package, beta plus 1 IB times RE. Okay, so what do we need to do now? We still aren't completely finished. What is missing? The only thing that's missing is IB. IB is missing. So how do we calculate IB? Well, we go with V again like we did before. And this time we have this as the only change between this V and the last V we were doing is that we now have beta plus 1 IB as both the collector resistor current and the emitter resistor current. And when we substitute there, we have 4 terms. Let's just do that and you'll see it. We have, so going from left to right, we have beta plus 1 IB RC plus IB RB plus VBE is the voltage across there plus beta plus 1 RE. So beta plus 1 RE, 1 voltage, 2 voltage, 3 voltage, 4 voltage to get to V. So that voltage plus that voltage be the voltage between the base and emitter, then the voltage across that, then the voltage across that, and they add up to V. So all we need to do now is simplify by gathering together like terms. We bring the VBE over on the other side. We extract the IB from the others. We simplify there. We have that. So we use brackets to our advantage to make the equation simpler, collect up the terms, and therefore now when we divide by that, we end up with IB. So that becomes our IB equation for this part of it. Well, guys, that's it for today. I mean, thank you for watching the Stephen Mendes channel, and more specifically, our biasing the BJT video. We'll see you soon again in the next video.